Greetings. Welcome to the exercises video associated with section or lecture 1.5, Measurement, Uncertainty, Accuracy, and Precision in the General Chemistry Lecture Series presented by the Evidence Reasons Academy. I have the word arduous in big red letters because if you found the last lecture arduous, I can sympathize because if you watched it, let me assure you that it was also difficult for me to give. I almost fell asleep in my own lecture, delivering the lecture because the material was tedious. So I really want to salute everyone that has joined us, that has listened to the lecture and is now joining us for the exercises. I often say, or I'm starting to say, that sometimes to dig and find buried treasure, you have to dig through a lot of dirt, and we were digging through dirt in the associated lecture, lecture 1.5. So if one wants to understand some of the issues that we're talking about at the Evidence and Reasons for the Christian Faith video channel, chemistry is going to be helpful, but some of the path to that buried treasures is not going to be pleasant. And so let me just give you a little encouragement to keep persevering. And I want to, again, thank you for joining me today. So let's do the odd numbered exercises first, because I happen to have the answer key, and so do you. If you just go to the link at the bottom of the screen there, and it's in the OpenStax Chem 2E book. So let's go right to it now. Well, if we have, if I'm not worn out, and if you're not worn out, we'll go through the even numbered exercises as well, but I won't be able to corroborate it with an answer key. And if I make mistakes or there are concerns, please feel free to post comments in the comment section of the video. It says here, express each of the following numbers in exponential notation with correct significant figures. Let me show you how I'm going to cheat a little bit with this using, I hope some of you are familiar with how to use spreadsheets. There's spreadsheets in Microsoft Office, and there's also Open Office. But I'm going to cheat here. I hope you can read what I'm doing in the spreadsheet. So we have 704, and in column C, so this is going to be the original. So I'm going to use the original notation. There's a word that they use for this. I guess it's just decimal notation or non-scientific notation. I don't know what the term is. They used a word in the lecture section for something that's not in scientific notation. But here's a little trick that may or may not help. Let's find out. Let's find out. So let's try to take a shortcut, because this may be actually, I know this may sound funny, but it is good to learn how to do arithmetic by hand. But are you going to do that the rest of your life, even professionally? If I were a boss, I wouldn't want my staff doing arithmetic by hand. I would expect them actually to be using calculators or spreadsheets. So just take it for what it's worth. There's benefit in learning how to do this manually, but professionally, you really, when it push comes to shove, you need to learn, you need to use the tools. The boss would probably prefer it. There is benefit in learning how to do things manually because it's just going to expand your mind and your facility with math. And that might be the only reason to do it manually if you have a way to do it electronically. So let's just try to do this first electronically, and then we're going to, just for practice and exercising your brain muscle, so to speak, we'll try to do it manually. So I'm formatting the cells, and I'm going to ask for scientific notation. And I could see already one of the problems is it's not going to give you the right significant figures, at least in this package. At least in this package. So we may not get the right significant figures. We'll just see. So I go to this cell here and I type a plus, and then I move my cursor to the left, and we'll see how it's stated in scientific notation. So let's try, and I'm going to do that for the other numbers too. C, D, E, F, G. So let's enter the numbers 0.03344. Yeah, it's not going to put the right number of significant figures. Let's see if I can increase this. Okay, so that didn't work out so well, did it? It's not even letting me add decimal places. It's not even letting me add decimal places. Unless I do this, let's see if I can add decimal places. Okay, so I learned a hard lesson here. It doesn't handle significant figures, at least in OpenOffice. So that'll have to be done manually, 22086. But the benefit is you'll at least get part of the scientific notation correct. You just have to fix the number of decimal places. This one's going to be painful because these are repeated zeros. So there's 1, 2, 3, 4, 5, 6, 7. 7 leading zeros. Let's count it. 1, 2, 3, 4, 5, 6, 7. 7 leading zeros. So 1, 2, 3, 4, 5, 6, 7 leading 0, 6, 5. G is 0.007157. So look, why don't I go ahead and fix the number? So given that we have at least part of the conversion, let's count the number of significant figures. Being able to do significant figures, one can learn it like trying to ride a bicycle. Sometimes you learn by doing, and I think that's really the best. Or you can read a manual on how to ride a bicycle. And that's what the last lecture was more like. It's almost easier to do, to learn it by doing. So for question A, 45A, 704 has 3 significant figures because you start from the left and you take the first non-zero number. If this is to the left of the decimal point, and you just count up until the decimal point, provided there are no trailing zeros. Okay, so that was really long-winded, but it's easier just, if you do it enough, you'll just start to see it. So I see 3 significant figures, and over here, if you can see my cursor here, you could see this is expressed with 3 significant figures, 7.04. The nice thing about scientific notation, it's very clear about the number of significant figures. So this is 7.04, and the E plus 002, it could also be stated as 7.04 times 10 to the second power. So it means the same thing. It's just some of the notations just a little bit different. The next one, we ignore any zeros immediately to the left, any continuous, what we call leading zeros. So if the number to the left of the decimal point is 0, and then any zeros immediately to the right, or any contiguous block of zeros immediately to the right of the decimal point, are considered leading zeros, so you don't count them when you're counting significant figures. So the significant figures are 3, 3, 4, 4, so that's 4 significant figures. And the scientific notation is 3.344 with the right significant digits. So given that I just did this electronically, I'm going to show how it can be done just from a conceptual standpoint, how to do it manually. So let me just move things around here so we could see things a little more clearly. So if we have 704, what we do, let's see if I could do this with shapes. What we want with scientific notation is to have only one digit to the left, only one digit to the left of the decimal point. So that's the goal. Let me just give this extra weight. Maybe I'll put a decimal point in. Let's see. I'm trying to figure a way that I can help visualize this. So please forbear with me, because I really want to try to help. If we could do it with one example, it might really help to be able to visualize what's going on. So just imagine that we're going to try to move the decimal point to the left so that only one non-zero number is to the left of the decimal point. That's the goal of scientific notation. We're going to try to get one non-zero number to the left of the decimal point. In fact, just to help the process along here, I'm going to make this even bigger. Now, I'm not going to do this for each and every one, because what I'd encourage you to do is, if you feel you need practice, either use the answer key or use use a spreadsheet to help you practice doing scientific notation. And as I said, that might be just good as an exercise, but if you're doing things professionally, it's probably a good idea to use the electronic tools like calculators and spreadsheets to help you do this. So the goal is to move to first take that number and move the decimal point to the left such that you have one non-zero number to the left of the decimal point. So let's count how many places we have to move the decimal point. We go from here, so move it one digit, two digits. And so the number of movements of the decimal point, the number of digits you move the decimal point across, so we're moving the decimal point across these digits, the number of digits we move it over is the power of 10 that we have to use when we use scientific notation. So remember, the proper format is to have one non-zero number to the left of the decimal point, and then the rest of the number after the decimal point, and the multiplier, the multiplier is 10 to the, and you count it 1, 2, 10 to the second power, which is the number of movements of the decimal point across the digits, the number of digits you have to move the decimal point across. And so it should be 7.04 times 10 to the second power. Now, why don't I check the answer key? The answer key says 7.04 times 10 to the second power. Now note that a spreadsheet might use the might express it, instead of 10 raised to the second power, it'll say e plus 002 or something to that effect. It means the same thing. So maybe at least that helps get you acquainted with how it will look, some of the different ways that it's the same thing is represented. So now let's go to the next exercise. And that is 0.03344. Now we know the answer ahead of time, but let me just clean this up. What was it? 0.0. Ooh, didn't like that. Zero point zero 3344, and let me clean this up. So again, what we're going to try to do is move the decimal point so that we have one non-zero number to the left, only one non-zero number to the left. So to do that, we have to move the decimal point. See if that, okay. We move the decimal point. Let me get this a little better here. We move the decimal point across 1, 2, and 2 digits. Now, I just realized in the process of saying this, I was a little bit weak in using the proper terminology. There is terminology for all the parts of a scientific number, and let me just cover that. And I wish they'd actually covered it in the chem lecture, because then I would be able to use the right terminology. So this is an example of something in scientific notation. We have the coefficient, which is sometimes called the mantissa and sometimes called the significand. I think mantissa was the way I was taught. We call this number the mantissa. This is the base and the exponent. The base is almost always 10. So I'm going to try to use this terminology. I may use the word mantissa, If that offends you, use the word coefficient or significand. So what we wish to do is to convert the original number that's not in scientific notation, and there is a term for this, a number that is in this format. So I had to pause the recording just so I could look this up. And the term that they used in the lecture for numbers not in scientific format, like the one they're showing, is called decimal formatted numbers. I'm just going to use that term, decimal formatted number. So let's go back to the exercise. And so the decimal formatted number is 0.03344. And so that's the decimal formatted number. We wish to transform it into a mantissa times 10 to some integer power. And again, I'm getting that terminology from this picture where the term mantissa is synonymous with coefficient, synonymous with significand. So I had to pause this just to look it up. That's one of the benefits of pausing the recording. So we're going to convert the decimal formatted number into scientific notation. So the goal is to form the mantissa. So we take the decimal formatted number and we move the decimal point. In this case, where the number to the left of the decimal point is 0, we start trying to move the decimal point to the right to be able to form the mantissa. Remember, the goal in forming the mantissa by moving the decimal point is to make the mantissa have only one digit, non-zero digit, one non-zero number to the left of the decimal point. So we're going to try to do that. So we have to move the decimal point 2 positions. So we can just imagine here that we have a new decimal point. And so that would be 3.344. And how many did we move it? If we moved it to the right, that the integer then will be to the -2. So let me do that. Let me move. I'm gonna have to move everything. It's gonna be kind of agony here. It's okay. I have to move everything, shift it all over. So if we move the decimal point to the right, we have to use a negative integer for the exponent, and the magnitude of that negative integer is the number of places we've moved it to the right, and it's 2. And just to check, the correct answer is 3.344 times 10 to the -2. Okay, you can see that this is, maybe we'll go through one more example and then I'm just going to blast through the last ones because some of the viewers may already feel very comfortable doing this and they don't need practice, and it would just be torturous to go through it. Those who need the practice or who are pressed for time, I just encourage you to just use the calculator or just do, just do what you can. So we'll go through one more example. Let me see which example we should use. I'll use a more challenging example. I'm going to use a more challenging example. Let's do a couple challenging examples. So 547.9. The correct answer is, let me just give the correct answer. So let me try to do this in my five, 47.9. I'll just try to do this in my head. 5.479 times 10 to the 2. Yep, that's the right answer. So we have 4 significant figures. I have 4 significant figures here. I moved the decimal point 2 spots. So with practice, you'll be able to just do this like you're with being half asleep. And again, if it's tedious, if it's too tedious and you're doing this professionally, just use the computers to help you. So now let's go to a more challenging example. And that will be this one, 22086. 22086. Now I can just look at this. I'm going to eyeball it. I can say that I'm pretty sure it's going to be 2.2086. I'll just give the answer and then we'll just backtrack. That might be more efficient. Yep, that is the correct answer. So let's see how I did it. I think this is going to be easier if you actually see what the right answer is first and then kind of work our way backward. I think that's going to probably be the better way to teach this. And so part of me doing this exercise is learning how to teach this better because then I understand it. So the goal is to take the decimal formatted number, which is this, and create a mantissa and then an exponent. There. So to create the mantissa, we take, let me grab this decimal point here. I know this, half of this is just doing this, putting in the right symbols. And I'm going to grab some arrows. It's going to be painful. And the rest we're just going to skip through. I mean, just blast through. Oops. So let's count how many we have to do. How many moves of the decimal point we have to make. If the move to create the mantissa from the decimal formatted number is moving the decimal point to the left, remember the exponent will be positive. So let's move the decimal point across the digits. 1, 2, 3, 4. So that corresponds to the exponent here. And in doing that, we do create a mantissa with only one non-zero number to the left of the decimal point in the mantissa. There we have it. At least now I'm also using the correct terminology to describe all this. So let's find another number, 1000.00. This one's going to be a good exercise right here. So I'm going to skip a few steps because I don't want to be too tedious. So the number that we're dealing with will be 1000.00. Make sure I'm doing this right. We have how many significant figures? The important thing is if you have trailing zeros after the decimal point, those zeros, the last trailing zero is a significant figure. So anything between the last trailing zero to the very first non-zero number beyond the decimal point are significant figures. So we have 1, 2, 3, 4, 5, 6 significant figures. Let me count that in the mantissa. The mantissa here, this is the mantissa. Okay, so this is the decimal formatted number, and this is the mantissa. Let's count how many significant figures we have in the mantissa. 1, 2, 3, 4, 5, 6. So far so good. We got that right. And how many moves do we have? What direction and how many moves do we make at the decimal point? We have 1, 2, 3 to make that decimal formatted number into a mantissa. So since that was 3 moves to the left, the integer should be, the exponent should be to the 3rd power. And let's check the answer. The answer key says 1.00000 times 10 to the 3rd. So I got that right. That's encouraging. That's encouraging. So let's try another one. Let's try the next one. And this number will be challenging. It's going to be 0, either 2, 3, 6, 5, 1. So the hard part, first off, let's determine how many significant figures there are. The number to the left of the decimal point is a 0, so that doesn't count as a significant figure. Any 0 immediately to the right, or array of zeros immediately, or a continuous block of zeros immediately to the right of the decimal point are considered leading zeros, and we ignore those as far as counting the number of significant figures. So the numbers that count as significant figures are 6, 5, 1. So now let's count how many moves and what direction we have to move the decimal point. So we have 1, 2, 3, 4, 5, 6, 7. Did I do that right? 8? 8. We need 8 moves to the right. Since the move was to the right, the exponent has to be negative, and it's 8 moves to the right. Does that agree with the answer? And the answer is 6.51 times 10 to the minus 8th. We got that right. So you could see that some of it's going to be tedious, but again, like I said, there are ways you can do this electronically, and if you did this professionally, that's what you'd probably do. So So maybe this exercise is just to make one comfortable with what the concepts are, not so much that we're going to be walking calculators. Okay, so the next one is 0.0077157. See, and I just did that. So let's just double check our work. Decimal formatted number is this. The mantissa should look like that, where we have one digit, only one digit, non-zero digit to the left of the decimal point in the mantissa. To do that, we move the decimal point 1, 2, 3 to the right, and since it's a move to the right, the exponent should be -3. Moving to the right, the exponent has to be negative. The magnitude will be 3 because we had to move the decimal point 3. And the number of significant figures, again, if the number to the left of the decimal point is 0, it is not counted as a significant figure. And then a number to the immediate, the zeros immediately to the right, the either a single zero or a group of zeros immediately to the right of the decimal point are leading zeros and therefore not counted as significant figures. So the significant figures are here. So I'm just trying to show graphically what this should, to conceptualize all the parts. And let's verify the answer, 7.157 times 10 to the -3. Excellent. Okay. So let's move on to exercise. On second thought, I may not, if this starts to get too tedious for me, we may not even do the even exercise. We can give it a fair shot. So let's go to number 47. Maybe it won't be as bad. Indicate whether each of the following can be determined exactly or must be measured with some degree of uncertainty. The number of seconds in an hour is 60 seconds in an hour by definition, so it can be determined exactly. And let me check that. It is exact. B, the number of pages in this book. The number of pages is exact. There's no uncertainty, especially since, especially if you have a book that has number of pages, that makes it easy to count. You can count it manually. There's no uncertainty. It's what we call discrete entities, discrete objects, well-defined objects, and you can count individual objects. The number of grams in your weight. The number of grams in your weight. All of our measuring devices would have uncertainty because the exact number of grams cannot be practically determined. I mean, hypothetically, one could count all the atoms or whatever, but we don't have any means of measuring that. So that would be measured with some degree of uncertainty, and the answer key agrees with that. The number of grams in 3 kilograms. The number of grams in 3 kilograms is 3,000 grams by definition. By definition, anything that is by definition is exact. That means in a mathematical abstraction, anything by definition will be exact. So what that means is if you don't have to do a measurement to make it, if you can just state it because it's assumed to be true, then it's exact. The volume of water you drink in one day, that is uncertain. It's measured with some degree of uncertainty. The distance from San Francisco to Kansas City is the same thing. It's measured with some degree of uncertainty. And what I just said agrees with the answer key, thankfully. How many significant figures are contained in each of the following measurements? Since we've been going through these exercises, let me try to guess. Try to do it just in my head. This looks like 2, and the answer key says 2. This looks like 3. It's really nice if it's scientific notation, because the number of digits in the mantissa here, this is the mantissa, is the number of significant figures. That's one of the nice things about scientific notation. You can actually see the number of significant figures easily. This one has 5, 1, 2, 3, 4, 5. And answer C is 5. That's encouraging. This one has 4. Remember the trailing, again, this is scientific notation. All you have to do is just count the number of digits. And the number is 4. This one has 1, 2, 3, 4, 5, 6. We start with the first non-zero number beyond the decimal point, and in this case, the last number to the right of the decimal point. If you have a non-zero number to the left of the decimal point, just keep counting until you hit the last digit to the right of the decimal point. This one has 2 significant figures. That agrees with the answer key. This one, it's a little subtle. You, as far as I can tell, as far as I remember, you always count the number of trailing zeros as significant figures if it's to the right of the decimal point. So that's 1, 2, 3, 4, 5. I got that right. And I think if one looks in the lecture, in the OpenStax lecture, it'll indicate that too. You count the number, you count it as a significant figure if the 0 is trailing and to the right of the decimal point. Count it as a significant figure. Okay. Round off each of the following numbers to 2 significant figures. So we're going to round to these 2. Since it's a little obnoxious there. Apologies. It's not letting me do this nicely. See, I'm just trying to highlight 2 of them and it's not letting me do that. So these are the 2 numbers of interest here, and it keeps highlighting 2. I'm sorry. This is really obnoxious here. So 0.4, and then the last significant figure, whether we round up or down depends on the number to the right of it. If it is greater than 5, we round up. So this would be 0.44, and the answer is 0.44. This one has 4 significant figures. We really don't need to do any rounding. We just have to drop the trailing zeros, so it would be 9.0, because this would be the 2 significant figures there. And since the trailing numbers are all zeros, we don't have to do any rounding. And the answer is 9.0. That's encouraging. 2 significant figures here. And since the first non-significant digit number is 2, we round down. So we could, what we call in the computer world, we just truncate. We can just truncate off the 2. They call that rounding now, and we can also call it truncation. The answer is 27. And the answer key says 27. This one should be 1, 3, and then the trailing 0 here the trailing number, the final number should be a 0. It should be converted to a trailing 0. Since that number is 5, the last significant figure is rounded in a way that it should be made even. So the question is if the first insignificant number is a 5, do you round the last significant figure up or down? If that number is odd, you round up. If that number is already even, you can round down. So in this case, we're going to round up. It should be 140. So the answer is 140. This one should be easy. That should be 1.5 times 10 to the minus third. And this one should be 0.44. So we have these two significant figures here. The first insignificant figure is 5. And in that case, according to the rules, if the last insignificant figure is an even number, just drop the 5. And that's provided there are no non-zero numbers after the 5. But again, as I'm reading off these rules, after a while, it'll be just like riding a bicycle. You don't think about it. And as I was trying to emphasize professionally, just use a calculator to get it, to help you get it right. Maybe getting the significant figures is, the number of significant figures is probably a little challenging, but the rounding should be done automatically by your software. And same with the conversion to the scientific notation. So that's all. Let's see if that's everything for the odd number exercises. Oh, we still have some more. Let me just see how many more we have. Okay. We have this one. Perform the following calculations and report each answer with the correct number of significant figures. So now, in between the lectures, let me save this. So this should be 53. So we have the inputs 628 and 342. Each of them have 3 significant figures. So we take the number with the least number of significant figures and use that number of significant figures to give us how many significant figures the final product should be. So we call the inputs 628 and 342 as factors. So this is a factor. This is a factor. And when we multiply them, the result, the proper term is to call it a product. So hopefully you could see how I did this in this spreadsheet. Let me just do that again. So you type in the numbers that are input, really the factors, go to an empty cell, type a plus, move your cursor to the first input number, type a star, and go to the next input number, and then press return. So practice will help you do this. Now the way we could do this multiplication in a spreadsheet, and I encourage people to try it with a spreadsheet. The way it works in this spreadsheet is if you wanted to type in 5.63 times 10 to the second power, you type in 5.63 E2. That's just the way it works there. 5.63 E2. And then 7.4 times 10 to the third, you type in 7.4 E3. Really, that the E is exponent and 3 is indicating what that exponent is. There are two significant figures here, so the answer should be expressed in two significant figures. And so I'll do that. So I go to an empty cell. I type a plus. I take the first factor there by moving the cursor, and then type a star, and then move the cursor to the second factor. And the result has lots of significant figures. We should only take two significant figures. So you see if I could do a quick format this way. Scientific. And we want two significant figures. Let's see if it's going to round it correctly. It should be with two significant figures. That should be 4, 2. So let me see if I can do this with two significant figures. 4.2 times 10 to the 6th power. Let's see if that, first of all, let me do, that was question A, this is question B. Let's see, question A. Oh, it wanted it in scientific notation. Apologies. This wasn't even correct in scientific notation. So let me reformat this in scientific notation. And it wants 3 significant figures. So I specify that by putting the number of zeros in the format code to have the number of significant figures. And it's 2.15 times 10 to the 5th. Let's see if that agrees with their, yep, theirs is 2.15 times 10 to the 5th. Now, what was the original number? Let me go back to the decimal formatted number. It was this. We could walk through the painful steps of first rounding it. So the question is, do you round it first, or do you make it the scientific notation first? I don't know that it really makes any difference. But since we've already gone through these composite exercises, perhaps I'll spare the viewers going through all the painful steps. We could do it manually, but I think we're probably pushing time limits in terms of exhaustion. So let's do C. We have the numerator is 28.0. The denominator is 13.483. And so we can call this 28.0 the numerator, the denominator. And the resulting decimal formatted number can be calculated by going to an empty cell, typing a plus, and then pointing to the numerator, typing a slash for division, and then going to the denominator. And we get 2.07 as the answer. I'm going to format that number in scientific notation, but note there are only 2 significant figures. So if we were going to round this off, it should be 2.1 times 10 to the 0th power, because we're not having to move the decimal point at all. We can double check this, thankfully. with the computer, and it's 2.1 times 10 to the 0th power. I think, let me see if they want it with that 10 to the 0 power. Oh, 28.0. Okay, so I didn't see that. The spreadsheet actually messed me up. It's 28.0, so that's 3 significant figures. So in that case, I don't round. My mistake. And see if I could, no, it won't let me do it that way. I have to reformat it. See, sometimes the spreadsheet will do some formatting for you that you may not like. So at least in this spreadsheet, by the way, in this spreadsheet, the way I enter the number of significant figures is to go into this format coding. It may be different in another spreadsheet. It did the rounding for me. So anyway, it would be just manually looking at this with 3 significant figures. We round, the first non-significant figure would cause us to round this number up. So it would be 2.08. And does that agree with the answer key? 2.08. And maybe to be complete, it should be 10 to the 0 power, just to emphasize this is in scientific notation. I don't know. I don't know what the convention is. The answer key says just a simple 2.08. So let's go to D. We have 8.119. I'm sorry, not 0.8119 and 0.000023. So this number has 4 significant figures. This one only has 2. Hopefully you see that. We're going to do multiplication. Again, just go to the spreadsheet, an empty cell, type in a plus, point to the first input, proper term is factor, type a star, go to the second factor, 0.186. That should round up to it should be 1.9. 1.9. Does it want it in scientific notation? Oh, that's the other thing. Let me see what this. Report each answer with the correct number of significant figures. I have to point something out. In this situation, it wasn't expressed in. This was not expressed in scientific notation. So I'm looking at the answer key. There's a little inconsistency in the answer key because the original numbers were not in scientific notation, but then they gave the number in scientific notation. That's not exactly correct. I'm sorry to say that. So I have a little disagreement with the answer key. So if we have only 3 significant figures, the proper answer then, if we use the original convention, would be 21500. 2, 1, 2, 3, 4, 5. Yeah, 215000. So, because sometimes the answers in the answer key are alternating between scientific and decimal formatted notation, and they're not being consistent in how they decide whether to go from one to the other. We could make an argument for either, but if we're going to preserve the original formats, if we started with decimal format, we should end with it. What'll happen is, what would happen if they're in mixed formats? I think the default would go to scientific notation. So answer B was in scientific notation, and let me see, the answer key there is in scientific notation. This one was in decimal format. And so we could express it in decimal format at 2.08, not going to scientific notation. This is in decimal format, not scientific notation. And we could just do a simple rounding to two significant figures, and that'd be 0.19. Now, if I were administering the test, I'd try to be a little bit more explicit, and I might not even dock points if you used one or the other. You just have to get the rounding correct and the number of, obviously the number of significant figures. So first to get the number of significant figures correct, and then the rounding. Of course, you have to get the multiplication correct. Now, I would presume, this is going to be a funny story, that the professor's going to let you use a calculator. In the olden days, when I was going to school, I had to use, I had a really nasty high school chemistry professor. She said, "I don't like calculators. I want you using slide rules." Oh my goodness. Mrs. O'Neill, I think you were a disgusting human being too. Sorry to have to say that. In addition to being a not very nice and informative teacher, you had a terrible personality. And I'm so glad I didn't have you many more sessions as my chemistry professor. You were not an inspiration. You were a terrible discouragement. And I'm sorry for all your students. So there you have it. And I don't think I had the privilege of putting that in your teacher evaluation. So anyway, just thought I'd say that. All right. E is going to be interesting because this is an addition. It's 14.98, 27340, 84.7593. Now what we do in a spreadsheet, we could just simply type the word sum and just highlight all the cells that you want to add. And what we're supposed to do according to the rules is the number, is the input with the smallest number of, we try to match the number of decimal places. We try to take the number with the least number of numbers after the decimal point and use that to tell us how many digits past the decimal point will report. Now there's a kind of a subtlety here because there's also there's some uncertainty how many significant figures are in that number. So there's 1, 2, 3, 4 for certain, maybe 5. So I will just suggest, let's try 27439 as the answer, since that's the same number of digits. It has the same number of digits after the decimal point, which is none, no numbers after the decimal point, as the input with the lowest number of numbers past the decimal point. Now, if they're persnickety about the number of significant figures, and we're going to just be on the safe side and say that there are only 4 significant figures, the number I might use is 27440, because I'm rounding that 39 to be just 40. So let's see what they say for E, 27440. Okay. All righty. That's one that has a little bit of a judgment call that was covered in, just for the sake of completeness, just so you know where I got that from. It says here, in cases where only the decimal formatted number is available, it is prudent to assume that all trailing zeros are not significant. So now let's go to the last in the numbered exercises. And that would be 42.7 and 0.259. By the way, let me just do a quick Google search on something. There was a nice little explanation of the proper terms to call the little parts of something. If we're adding things together, the two inputs are called addends. One or more inputs can be addends, and the result is called the sum. If we're subtracting one number from another, we subtract the subtrahend from the minuend, and the result is the difference. For multiplying, it's factor times factor, we get product. And here's another one with using the terms divisor, dividend, and quotient. And then there's the term remainder, but sometimes I'll just use the word numerator and denominator. It's been a long time since I've used these terms. Very rarely have I ever needed them, but just for the sake of completeness, I'm doing that. So let's do an addition. With the spreadsheet, it's 42.959. So we take the result according to the rules. If we're doing an addition or subtraction, we take the input that has the least number of digits after the decimal point, and use that as the guide for how many digits after the decimal point we'll report. So it should be 3 decimal points. I mean, only one decimal point, only one digit passed to the right of the decimal point. So let's round this up. Since just going back through the rules, do we round this number up or down? Since the first insignificant figure is a 5 and it's followed by a non-zero number at some point, we round up. So we round 9 to be 10, but we can't really do that. So we have to make this a 0 and then add that 1 to the next adjacent digit. And that number is 43.0. And again, I don't like the fact it does some of this automatic formatting. The number should be 43.0. That's my calculation, and that agrees with the answer in the answer key. So we're going to skip this one just for now. Now, I looked at this exercise and I have to complain a little bit. It's very hard to eyeball this. Very hard to eyeball this, especially for part C. So let's just try to do it, do the exercise. Which archer is the most precise? I'd say it's archer X because the arrows are landing very close together here. The closest together packing is right here. Which archer is the most accurate? Well, unless we have precise measurements and we're able to do a mean, we're just going to eyeball it. I would say this one, because it seems like the average location, if we average where all the arrows landed, it would be maybe about right there. So I'd call that the most accurate. Which is the both least precise and least accurate. Both these are not precise, and it's hard to tell which is the least accurate. And I'm just going to defer to the key, and it's saying archer Y is the least precise and least accurate. I have just a little issue with that because this one would look, to me anyway, to be leaning a little bit to the right. And so I don't think that's a good without mean and variance numbers, trying to throw that on some poor student on a test, I don't think is fair. Just need to share my opinion on that. The best way to do it is to have numbers. I just don't think that's a fair question. So that's it for the odd numbered exercises. So just going back to this one, because it really bothers me. They said this is the one that's the least precise and least accurate. Maybe I'll just go see if I could blast through the even numbered exercises. Okay, express each of the following in scientific notation with the correct significant figures. That would be 7.110 times 10 to the second power. This is 2.39 times 10 to the minus 1. This is 9.0743 times 10 to the 10 to the fourth. This is 1.342 times 10 to the second. This is 5.499 times 10 to the minus 2. This one is a little, oh no, this is clear. This is 1.00000 times 10 to the 1, 2, 3, 4, 10 to the fourth. This one is 7.38592 times 10 to the minus 1, 2, 3, 4, 5, 6, 7. Okay. See if you practice this, you'll be able to do this. Indicate which of the following can be determined exactly or must be measured with some degree of uncertainty. The number of eggs in a basket that was covered in the text, it is exact. The mass of a dozen eggs is uncertain if it has to be measured with a scale, because these aren't discrete quantities. The number of gallons of gasoline necessary to fill an automobile gas tank, that is definitely uncertain. The number of centimeters in 2 meters by definition, that would be 200 centimeters. So that's exact. The mass of a textbook is uncertain. The time required to drive from San Francisco to Kansas City at an average speed of 53 miles per hour, that is uncertain because we don't know the distance with certainty. How many significant figures are contained in each of the following measurements? A is 3, B is 1, C is 1, 2, 3, 4, 5, 6, 7, D is 1, 2, 3, 4, 5, 6, because this is scientific notation, it's easy. This is 3 significant figures because the trailing 0 is after the decimal point. This is 1, 2, 3, 4 because we have two non-zero numbers and 2 trailing zeros after the decimal point, and we ignore the leading zeros. Let's see. The following quantities are reported on the labels of commercial products. Determine the number of significant figures in each. This is 2 significant figures, 2 significant figures, 1 significant figure, 2 significant figures, 3 significant figures, 3 significant figures, 1 significant figure, 4 significant figures. Remember the trailing 0. Okay, so after a while, it's just like riding a bicycle. You'll get through this. Round each of the following numbers to 2 significant figures. This will be 520. This will be 86. This will be 6.4 to 2 significant. This will be 5.0. This will be 22. This will be 0.89. Perform the following calculations with the correct number of significant figures. And again, we'll just use the calculator here. So this will be 62.8, 34. So it wants, this one will want two significant figures, so that should be 2100. That's my answer. Again, I'm just blasting through these. 0.0066 and 012. We want to add them all up. So this should be the one with the least number of places past the decimal point. So I would say the answer is 0.166. I think it's 0.166. So this is A, this is B, C is 3895, 1.792. So I'm going to multiply all three factors, that times that times that. The least number of significant figures, they didn't want it in scientific notation, is 2, so I say 65, like that. 6,500. B, 8.78 times 0.0500 and 0.478, just for completeness. So we take this times this divided by that. And we have three significant figures here, three significant figures here, three significant figures here. So the answer should be with three significant figures, and that will be 0.918. And that was, did I skip one? 62, 147, 38. Oh, I missed one. Apologies. So this is 15 minus 0.15 minus 0.6155. So the answer is this minus this minus this, and we want zero digits past the decimal point because the figure with the least number of digits past the decimal point is this number here, and it has zero digits past the decimal point. So the answer should be 15. I'm sorry, should be 14. Apologies. And we already did E. I just used the wrong, I got it out of order. So I have 140, 7.68, and 0.014. And we're going to add all these numbers up. We could do that with a quick sum. And the number with the least number of digits after the decimal point has zero digits after the decimal point. So if we do our rounding, the answer should be 148. G, 28.7 minus 0.0483, 0.0483. I'm a little bit dyslexic, if you can't tell by now. I have to be a little careful of that. And the maximum number of digits after the decimal point is the least number of digits past the decimal point has only one digit past the decimal point. So we're going to round off so that we only have one digit past the decimal point. And so the answer is, surprisingly, 28.7. So this little amount that was subtracted from it is considered negligible enough to just leave the the term the minuend. The difference is the same as the minuend. This is the minuend. This is the subtrahend. This is the difference. Okay, so H, we have 88.5 minus 87.57 divided by 45.13. Yikes. Okay, this is going to be composite. So first we'll do the subtraction. 88.5 minus 87.57 divided by 45.13. So the result of this should only have one number past the decimal point. So let me break this apart. I'm going to go over here and say 88.5 minus 87.57 is equal to 0.9. Do you see how this minus this results in 0.93, but there's only, it says to only, in that case, retain the number of digits past the decimal point of the input with the least number of digits past the decimal point. And so we only have one significant figure when we do this subtraction. So you do the operation first on the numbers inside parentheses. And since there's only one significant figure, we're going to make this number have only one significant figure, and that's 0.02. That's my best answer. That would have been an interesting one to look at to see what their answer was. Finally, we get to the last question. Classify the following sets of measurements as accurate, precise, both, or neither. Checking for consistency in the weight of chocolate chip cookies. Checking for consistency in the weight of chocolate chip cookies. This is such an open question, but I would say this is not accurate and it's not precise. They're all over the map. This is uncertain because they don't tell us what the correct number should be for accuracy. So I have some problem with that. So if they're checking for consistency, we're only looking for precision. It doesn't look very precise to me. We could say this is, and I don't like the framing of that question, sorry. Testing the volume of a batch of 25 milliliter pipettes. Okay, so the pipette should be 25 milliliters. We can tell if this is accurate. So 27, 26.99, 26.97, 27.01. This is, first of all, if this is 25 and only two significant digits, we have some very, these are giving very nice figures. I'd say this is precise, but it's inaccurate because it should be closer to 25. Ideally, the mean of this equals this, and the variance about the mean is also evenly spread out to the left or right of 25. If we plotted this, determining the purity of gold. So 99.99%. Well, you can't get higher than 100%. So this is, I'd say this is accurate and precise. I'd say it's accurate and precise because we have just differences here. You have two that are even repeated here. Actually, two of the numbers repeat and the other two numbers repeat. So I'd say it's accurate and precise. I do have to say something here. The word accurate, I just realized it's a little bit, it's subjective to say when something is accurate or inaccurate. It's the degree of accuracy that is more important to state. We normally say it's accurate within this amount. The precision is this thing, but to say it's accurate or precise without specifying the degree of accuracy or precision, I think that's sloppy language. So again, I'm just going to be, I'm going to throw some criticisms at the text here, and that's perfectly fine. I think every text will have some things that will the reader might have some issues with, and I think it's perfectly fine to voice to be skeptical of what one reads and not necessarily accept it as being well worded. I'm not questioning the intents, but maybe the wording and the presentation may have some room for improvement. So again, I would really like, finally, I would really like to thank everyone who has suffered with me through this. It was a learning exercise for me as I learned how to express ideas better. And I'd like to thank everyone that has borne with me going through this. So with that, that completes the exercises associated with section 1.5 on measurement, uncertainty, accuracy, and precision. So with that, thank you, and that's it for this video. Take care, and God bless you.